So I'm going to be talking about this topic, union closed family of sets. So if the title is not clear right now, it's okay. By the end of the talk, it should be. So a set is a well-defined collection of objects. By well-defined, I just mean that there should be no ambiguity or confusion about what exactly should be the elements in your collection. So I mean, you guys have already seen, examples of set. This is a set, right? Because these are points in our square such that this condition is satisfied. So there is no confusion about what pairs you should be taking. Other examples are, set of natural numbers you just saw, and I could take the alphabets in the English language. A family of sets is just a collection of sets. So, I can take a collection of sets. These are two sets that I've taken in the first family, or I can take, a collection of all natural numbers and the collection of integers. And, you can write them as a list. You can write them inside curly brackets. You can write them however you want. So, the union of two sets is a set that contains elements that appear in either of the two sets, and it's denoted by this A, U, like a U symbol, B. So the example is you have 1, 2, 5, 6 and 4, 5, 8, 7. You put them all together, you get 1, 2, 4, 5, 6, 8, 7. So, as a Venn diagram, this is known as a Venn diagram. It looks something like this. So a family of sets is said to be union closed if the union of any two sets from the family belongs to the family. That means, so this is an example of a union closed family. You take any two sets from the family and check if that appears in it. So these are three families. So the first one is an phi, that is the symbol for empty set. So it's a set with 0 elements in it. So there is nothing really to check. The second one only has one set, again nothing really to check. The third one has two sets in it. So now you just check whether the union of the first set and the second set is in the family. So what is the union of 1, 2 and 2? It's just, so what do you think you will get when you put together 1, 2 and 2? Yeah, you'll get 1, 2, and that's the first set, so it's already in the family. As a non-example, you look at this family of set 1, 3 and 1, 3, 5. That is not union closed because if we take the first two sets, you'll get 1, 3, and that is not part of the family. So now finally we can state the conjecture. A conjecture is just a guess. We don't know if it's true, we don't know if it's false. So the conjecture is that given a finite union closed family of sets, other than the family containing only the empty set, so you don't consider the family containing only the empty set, there should be an element that belongs to at least half of the sets. Okay, so this was first formally stated by this mathematician called Peter Frankel in 1979. So it's been decades and we still don't know whether this statement is true or not. Sorry. So this is an example. So we have this union closed family of sets. So can you pick out elements that occur in at least half of the sets? You can say that this is a family of 5 sets, and 2 belongs to 4 sets and 3 belongs to 3 sets. So there are elements that belong to at least half of the sets. And such elements may be called abundant elements. Elements that appear in at least half of the sets are known as abundant elements. So an exercise in set theory is an equivalent formulation of this conjecture. So the intersection of two sets is denoted by this A inverted U B, which contains elements appearing in both A and B. So I think you guys already saw, the intersection of two curves. And I mean, from our previous example, there's only one element that belongs to both of the sets. It's 5. In the Venn diagram, it looks like this. The universe is the union of all sets under consideration. Here the universe would be the union of all sets in the family. And the complement of a set are elements of the universe which do not appear in A. Okay, so I mean, you can just look at the Venn diagrams and you can see that the complement of 1, 2, 5, 6 is all the elements except for the elements which appear in the set. And the universe is just everything. You take the union of all the sets in the family and you get the universe. So in exercise in set theory is to show that the conjecture we just stated is true if and only if this statement is true. That for a given family which is intersection closed, there is an element that appears in at most half of the sets. So there we had a union closed family and we said there is an element that belongs to at least half of the sets. Now it's like a dual of that. Okay, so there are some partial results and facts that we have. If we put some limits on the number of sets that we have in our family, or we put a limit on the number of elements that is in, say, our universe, then we have some partial results. I think the conjecture is proven for families which contain at most 46 sets, and it's also true for families where the universe contains at most, I think, 11 elements. So we have partial results, but that's not really that significant because the conjecture, our guess is that it should hold for any number of sets, right? And so lower bound, what I'm calling lower bound, is basically the ratio of sets where at least one fixed element should occur. So right now in the conjecture, that ratio is half. We want an element to occur in at least half of the sets in the family. So there have been lower bounds which are in terms of the size of the family of sets. So it's not independent of whatever we're considering. In our conjecture, it's 50% or half for any family of sets. But people have given results where the lower bound is in terms of the size of the family of sets. And another question is, cannot this lower bound be more than half? Can we say that, okay, I want the conjecture to be that there must be an element that appears in at least 60% of the sets, or 2/3 of the set? We can't have that, because if you look at families like this, then every element occurs in exactly half of the sets. So this 50% bound is sharp. That means that you cannot increase it further, because if you did, then there are readily available counter examples. Okay, so another partial result is that if F is our union closed family of sets and the smallest set of F is a singleton, then X has to be an abundant element. That means that X has to occur in at least half of the sets. So how do you go about proving something like this? So you break your family into two subfamilies, two smaller family of sets. You take the collection of sets which contain X, and then you take the remaining one, which is family of sets which do not contain X. And you realize that if you take a set in F2 is the family of set which do not contain X, then if I just add X to any set in F2, then that has to belong to F1. Why is that? Because F is union closed. So if I take the union of any two sets in F, it has to belong to F, right? So this thing, if maybe I'll write here. So if I send A to A union X, then this is actually a function from F2 to F1, okay? And notice that if I have A union X equal to B union X, then A has to be necessarily equal to B. Why? Because X does not belong to A, X does not belong to B, so it's just the remaining elements, right? So what I've said is that for every element in F2, there is an element in F1, right? So if this is my F2 and this is my F1, what I've said is that if I have these many elements here, then at least there are that many distinct elements here. There may be more, but at least there are that many. So what does that tell us? That tells us that if this is the number of sets in F2, that has to be less than equal to the number of sets in F1. And we're done, because we partitioned the family into two parts, and we're saying that F1 has to contain more elements than F2, then that means F1 is the family of sets which contain X. So X has to belong to more than or at least than half of the family of sets, half of the sets of the family, sorry. Okay, so this is an example of what we just did. If this is our family, you break it into things that contain 1 and things that do not contain 1. And then we have the following correspondences. This is the correspondence. Okay, so the set 2, 3 just goes to 2, 3 union 1, which is 1, 2, 3. Okay, and then you see that, I mean, here you can just count, but if you do it for a general set, what we have proven is that at least for every element in the first family, there is a distinct element in the second family. Okay, so in late 2022, there was a big breakthrough in this problem, where somebody known as Justin Gilmer was able to obtain a constant lower bound. So this lower bound does not depend upon the size of the family, nothing like that. And the lower bound is of 0.01, that is 1%. Okay, so he showed that if you have a union closed family of sets, then there must be an element that occurs in at least 1% of the sets. Okay, and what he used to prove this is something known as information theory. Now, information theory is it's like a mathematical study of communication of information or quantification of information, storage of information, but it's formalized in the language of mathematics. So, and it was developed by a mathematician known as Claude Shannon, and the major thing that he realized was that the more surprising an event is, the more information it gives you. If I were to say something like in the month of May, Chennai is going to be hot, then it's almost like at that point I might as well just stay quiet, because nobody needs to hear that. You guys know that in month of May Chennai is hot. So nobody is getting any information out of it. But if I were to say something like in the month of November a cyclone is going to hit Chennai, then that is valuable information for people, because that's not very likely to happen. That doesn't happen every year. So the key point is that the more surprising an event is, the more information it gives you. And a key measure in information theory is entropy, and it's the same entropy that you just heard about. And a measure of information is known as information content. So information content is a function which increases as probability decreases, for the same reason that I just described, because probability is a measure of how likely an event is, right? Higher the probability is, the more likely an event is to happen. So, and we just learned that the more likely an event is to happen, the less information it gives you. So information content needs to be a function that increases as probability decreases. So this is how the information content is defined. You can see the formula there, and the expected value of information content is entropy. Expected value just means like, so if say I have this function from a set to 0, 1, this is known as a random variable, which is a function from all the set of values it can take to 0, 1, which are the probability of each say value in this. Then expected value of x is p of x, and okay. So I want to know the expected value of the information content, then that's just right. So this is entropy. It's denoted as h of x. So, but what does this all have to do with what we're talking about? We were talking about union closed family of sets, and suddenly we're talking about entropy. Well, the point is that, and this is now going to be very vague, it's not at all rigorous, but the point is that when you have a union closed family of sets and you have two sets, you expect the union to be in there. You know that if I have, if I have a family of sets, I have A, I have B, then A union B, I expect it to be there. Meaning, I expect A union B to give me, less information than A or, B. But what Justin Gilmour was able to show was that if there is no element that occurs in even 1% of the sets, then the entropy of the union will be more than or equal to the entropy of a single set of the union. Which is, how he does it is the whole proof, which I won't go into that, but that's basically it. So this is a contradiction because we know this fact to be true, but he was able to show that if there is no element that occurs with even 1% of the sets, then this is true. So that is a contradiction. So we know that there is an element that occurs in 1% of the sets. So these are some of references that you guys can check out. So this is Justin Gilmour's paper that you can read. Also, the second one is a polymath project. So a polymath project is like a collaborative project between mathematicians and students where you can take something like this, something which has been unsolved for almost 50 years, and longer than 50 years, and you can try to attack it from different, mathematicians can come together, students can come together, and they can try to figure out an answer. So they tried it with this and they came up with some partial results and some, some related results. They weren't able to prove it, but yeah, so this is something you can check out, and they have more projects about more conjectures and other sorts of problems. And they also have a Polymath Junior program for specifically for school students. And the third one is just like a very long expository paper on this conjecture where you can read, all sorts of details about it. So that's it, and I'll be very happy to answer any questions that you guys may have.